This is going to be the lecture over both Chapter 20, Sections 1 and 2. We're going to be discussing magnetism, fields, and forces. So the summary here is going to be that a bar magnet has a north pole and a south pole. Two opposite poles are going to attract each other, and two like poles are going to repel. The moving charge creates a magnetic field in the surrounding space. A moving charge or current is going to experience a force in the presence of a magnetic field. The direction of the force is given by the right-hand rule for magnetic forces, and the magnitude is going to be given by equation 20.1. And we're going to go over that. So you have a charge here, it's moving with this velocity. The magnetic field, which is going to be represented with the letter B, is pointing in this direction. So when the velocity is this way, the magnetic field is this way, it's going to experience something along the lines of torque, in that we're going to take a cross product and then the force is going to be occupied here with the right-hand rule. We'll go over that. So first, let's go here. There's a small discussion here regarding magnets and when they were discovered. If you take a look at this, 2,500 years ago is when magnetic phenomenon was first observed with magnetized iron ore. It was discovered that when iron is brought into contact with a natural magnet, then the rod also becomes magnetized. When it's suspended by a string from its center, then it tends to line up in a north to south direction, like a compass needle. Magnets have been used for navigation since the 11th century. Magnets of this sort are also called permanent magnets. You may have seen a magnet like this. One of the strongest magnets I've ever seen is something that came out of a cyclotron. So here it's picking up the steel filings and not the copper ones. And we'll determine why that is a little later on. So before the relationship of magnetic interactions and moving charges was well understood, the interactions of bar magnets and of compass needles were described in terms of magnetic poles. The end of a bar magnet that points towards the Earth's geographic north pole, which marks the axis of rotation, is going to be referred to as the north pole or end pole, and the other is going to be the south. Two opposite poles attract each other, and two like poles repel. Cutting a bar magnet in two does not give you two isolated poles. In other words, when you cut a bar magnet in half, you don't end up with what's called a monopole, or just a one-pole magnet. Instead, each half ends up with a north and a south pole. That's just how it works. So, differing from electric charges, magnetic poles always come paired and cannot be isolated. Like, you can have a positive charge existing out in the middle somewhere without having to have a negative charge go along with it. The same cannot be said of magnetism. It just doesn't work that way. The compass needle points north because the Earth itself is actually a magnet. Its geographic north pole is close to a magnetic south pole, as shown here. So you got the Earth, you've got N, you've got S, and then you can see how the magnetic field lines circle around. So the geomagnetic north pole is actually a magnetic south pole. It attracts the north pole of the compass. So, which that would make sense. If you, let's say you're here in North America, you have a compass and it points north, then the north pole of that is actually attracting the magnetic south pole here, which is located in the north pole. That's great for confusion, isn't it? So magnetic field lines show the direction of that a compass would point at a given location. So you can see it emanating from the north pole, and then the field terminates at the south pole. Just like the electric charges they emanate from a positive charge and end up converging onto a negative charge. So you can think of it sort of that same way. The Earth's magnetic field has a shape similar to that produced by a simple bar magnet. You have the core of the Earth that's in motion, so it's not quite as simple as that. Although permanent magnets are familiar to us, most of the magnets in our lives are electromagnets, in which magnets are produced by an electric current. Every appliance you own has an electric motor containing an electromagnet. The phenomenon of electromagnetism was discovered in 1819 by Hans Christian, I always murder that last name, Ørsted, who observed that a compass needle was deflected by a current-carrying wire. A few years later, it was found that a moving magnet near a conducting loop caused a current in the loop, and that a changing current in one conducting loop can cause a current in a separate loop. So we'll get to all of that later. When the wire carries no current, the compass needle points north. When the wire carries a current, the compass needle deflects. The direction of deflection depends on the direction of the current. So if the current's going this way, then you can see some deflection here. If it's going that way, then you can see some deflection here. That's why you never try to get compass bearings when you're standing under power lines. That's a very, very bad thing to do because it will lead you astray. So we know that electric and magnetic interactions intertwine. The Earth's magnetism results from electric currents circulating in the molten core. A compass needle points north because the Earth itself is an electromagnet. The Earth's outer core is made of conductive molten metal, which carries large electric currents while also circulating slowly. So that field is going to change over time, and geologic evidence shows that the magnetic poles wander relative to geographic poles. In other words, they don't line up perfectly all the time. Indeed, the Earth's field periodically reverses, so that former north magnetic pole becomes a south magnetic pole. And historically, reversals have occurred on average a few times per million years. Currently, the Earth's field is weakening. We may or may not be approaching a reversal. So, organisms other than humans, ranging from bacteria to pigeons and even whales, can sense magnetic fields and use them for navigation and orientation. So let's go and let's take a look here at section 2. So to introduce the concept of a magnetic field, we're going to review the formulation of electrical interactions, chapter 17, which you can go and do, where we introduced the concept of an electric field. And we described electrical interactions in 2 steps. Distribution of electric charge at rest creates an electric field at all points in the surrounding space. And you probably remember the diagrams or pictures that display that. This electric field exerts a force, F is equal to QE, on any other charge Q that is present in the field. And we've actually gone through and calculated some of those. We can describe magnetic interactions in the same way. A permanent magnet, moving charge, or a current creates a magnetic field at all points in the surrounding space. This magnetic field exerts a force on any other moving charge or current that is present in that field. Like an electric field, a magnetic field is a vector field. A vector quantity is associated with each point in space, and we're going to use the letter B to represent that. So in the first several sections of this chapter, we're going to concentrate on the second aspect of the interaction. Given the presence of the magnetic field, what force does it exert on a moving charge or current? And then sections 7 through 10 here, we will return to the problem of how magnetic fields are created by moving charges and currents. So we can represent any magnetic field by magnetic field lines, just as we did for the Earth's magnetic field. So we're going to draw the lines. They're going to go from north to south. The more densely the field lines are packed together, the stronger the field is at that point. At each point, the field line is tangent to the magnetic vector field B. At each point, the field lines point in the same direction a compass would. Therefore, magnetic field lines point away from north poles and towards south poles. So if you've ever played with fillings on a sheet of paper and then hold a magnet beneath them, then the fillings are going to line up tangent to the magnetic field lines. And you can see those figures here, and they're produced by a permanent magnet and by configurations of current carrying wire. So you can see if you've got a north and a south pole, you can see how those magnetic lines line up here and connect. Here you've got two poles that are the same polarity, and the field lines are pointing away from each other. So between flat parallel magnetic poles, the magnetic field is nearly uniform. If you'll remember, the electric field on the parallel plate chamber had the same phenomenon. You have a little bit of bowing at the edges, which like you did with a parallel plate's electric field. But by and large here, within flat parallel magnetic poles, you're going to have a direct shot from one side to the other. So to represent a field coming out of or going into the plane of the paper, we're going to use dots and crosses. So the way to really think about this is to imagine an arrow. If you see a dot, you can imagine that an arrow is pointing at you. It's coming towards you. If you have a cross, that means it is moving away from you. You're seeing the fins of the arrow as it's moving away. So if the field is coming up towards you on the page, out of the page towards you, then you would put a dot. If it's moving into the page away from you, then you would put a cross. So a magnetic, you can see the descriptions here for the captions. These are magnetic fields of current carrying loops and a current carrying coil. And these are some other examples of magnetic fields. And you can see some similarities there. So how do we go about quantifying magnetic force? We know that the most fundamental manifestation of a magnetic field is the force that it exerts on a moving charged particle. What are the characteristics? Well, its magnitude is going to be proportional to the charge. If two particles with charges q and then 2 times q move in a given field of the same velocity, the force on the particle with charge 2q is going to be twice as great as that with just 1q. The magnitude of the force is also proportional to the magnitude of the strength of the field. If we double the field without changing the charge or the velocity, then the magnitude of the force doubles. The magnetic force is also proportional to the particle's speed. Now, it's going to be different from the electrical field force, which is the same whether or not the charge is moving. A charged particle at rest experiences no magnetic force. Furthermore, the magnetic force on a moving charge does not have the same direction as the magnetic field. Instead, it's always perpendicular to B and V, the direction of the magnetic field as well as the particle's velocity. And it's going to be proportional to the component of V that's perpendicular to the field. So it's a cross product. You may remember that from the torque. When the component with that component is 0, then the force is going to be 0. So figure 20.9 here shows these relationships. So we've got charge moving parallel to a magnetic field. It's going to experience no magnetic force. It doesn't matter if it's moving directly with the field or directly away from the field. A charge moving in an angle is going to experience a force. And that force is going to be Q times the perpendicular velocity times B, or VB sine of phi that's in between the two. A charge moving perpendicular to a magnetic field is going to get the maximum amount of magnetic force because the angle there is at 90 degrees. So this is a description of all of that. Force is going to, of course, be measured in newtons, and B is going to be measured in a unit called teslas. That's a new one. So you might want to write that down. This is an interesting little application of MRI. You may or may not know that an MRI is going to basically create a field that's going to take all of the hydrogen atoms inside of you and pull them to a certain point in the field. And then as they relax, or their orientation begins to change back to what it was, then we get pictures, and that's what's being produced here with an MRI. So how do we go about determining the vector orientation of the force? As shown, the right-hand rule for finding the direction of the magnetic force in a positive charge is going to be as follows. You put the vectors together at the tail. Now you imagine turning V in a plane containing both V and B until it points in the direction of B. So you're going to take this and rotate it towards this. You turn it through the smaller of the possible angles. In other words, you don't take it and wrap it all the way around this way. You take it and turn it towards the smaller part. The force then acting on the line perpendicular to the plane containing V and B. So using your right hand, curl your fingers around this line in the same direction. So in other words, this curls this way. If you take your right hand and curl it in that direction, this shows you which way the magnetic field is going to go, or which way the force is going to go. So these are all of the steps right here. So let's say you've got the velocity going this way, and you want to take your hand and put it in the same direction, put your fingers in the direction of the velocity and then rotate it towards B. If you were to do that with your right hand, please don't use your left. If you do that with the right hand, then it gives you the direction of the force, which happens to be this direction. Now, if the charge is negative, this is what happens if it's a positive charge. If the charge is negative, then you are going to be looking at the opposite of what is given by the right-hand rule, as if you needed anything else to worry about. So when the charge is positive, it'll go this direction. If it's negative, then you'll be looking at these situations. So positive and negative charges moving in the same direction through a magnetic field experience magnetic forces in opposite directions. Now, obviously, it's going to be the same charge, so the magnitude of the force is going to be the same if the velocities in the magnetic field are the same, but the directions are going to be different. So the definition of a Tesla is going to be 1 Newton divided by an ampere times meter. The CG unit of B, the Gauss, is also commonly used. It's a scaled down version of a Tesla. So instruments for measuring magnetic field are sometimes called Gauss meters or Tesla meters. So velocity selector. The fact that a magnetic force is proportional to the speed of the charged particle can be used to create a device called a velocity selector. Many applications, such as spectrum analyzers, require a beam of charged particles that all have the same speed. Unfortunately, common sources of particle beams usually produce particles with ranges of speed. So the velocity selector is essentially a filter that allows only particles with the desired speed to pass through. So let's take a look here. So we've got a source of charged particles. We've got some sort of regulation here going on here of the speed. We've got a charged particle, mass m, charge q, and speed v enters a region of space where the electric and the magnetic fields are perpendicular to the particle's velocity. So you got the electric field going this way. You've got a magnetic field that's going into the page. All of that is perpendicular to the speed of the velocity of the particle. If Q is positive, the electric force is to the left with magnitude QE, and the magnetic force is to the right with magnitude QVB. By adjusting the magnitudes E and B, we can make these forces equal in magnitude. So then the total force is going to end up being 0, and the particle travels in a straight line with a constant velocity. For 0 total force, we're going to need the sum of the forces to be equal to 0. So the force due to the electric field plus the force due to the magnetic field offset each other, and you end up with 0. Solving this equation gives you the ratio of E over B. So if you know what both of those are, then you know what the velocity of the particle is. So you've got the velocity of the electric field, and then you've got the velocity of the magnetic field going in equal and opposite directions, and then this is the free body diagram for a positive particle, and then you've got the velocity going in this direction. So only if a charged particle has this velocity do the electric and magnetic forces cancel. All other particles are going to be deflected. Finally, you've got Thompson's E over M experiment. This is a pretty important one. So you've got Sir J.J. Thompson using basic principles of the velocity selector, which we just went over, to measure the ratio of charge to mass for the electron, which is what you're looking at here. The speed of electrons in a beam were determined from the potential difference used to accelerate them, and measurements of the electric magnetic fields enabled Thompson to determine the ratio of electric charge magnitude to mass in the electrons. So the charge and the mass weren't separately measured until 15 years later. With this experiment, he found that all particles in the beam had the same value for this quantity, and that value was independent of all materials used in the experiment. The independent shows that the particles in the beam, which we now call electrons, are a common constituent of all matter. So Thompson is credited with the first discovery of a subatomic particle, the electron. 15 years later, Robert Millikan succeeded in measuring the charge of the electron. That result, together with this, enabled him to determine for the first time the mass of the electron. And that's where it stands today.